So welcome back to Technology and Programming for Mathematics. In the next few assignments, we are going to be working with series approximations for functions. And these will extend the idea of tangent line approximations that we learn about in Calculus 1. Okay, so let's start by reviewing that idea. So we of course know one of the fundamental parts of calculus is the operation of differentiation, and one of the interpretations is that the derivative tells us the slope of the tangent line. Okay, so if you have a function y equals f of x and you want to find the equation of the tangent line, you can start by finding the slope of the tangent line. So you have to differentiate your function and then evaluate that derivative at the point in question. Okay, so let's look at a quick example right here. Let's say we want to write the equation of the line tangent to f of x equals square root x at the point x equals 9. Okay, now of course we remember that square root x is x power 1/2, and then we can differentiate using the power rule. So we get f prime of x equals 1/2 x power negative 1/2, right? We know that exponent comes down, becomes our coefficient, and the new exponent is 1 less than the old exponent, so we take 1/2 minus 1, get negative 1/2. Sometimes we would write it like this. Right. We remember that a negative exponent means it's actually a reciprocal. Okay, so x power negative 2 would be the reciprocal of x power 2. X power negative 1/2 would be the reciprocal of x power 1/2. So we got that. Okay, so the slope of our tangent line, since we're dealing with x equals 9, we'll plug that value in. And we get, I'll just jump to the punchline right there, right? So if you plug in x equals 9 right there, square root of 9 is 3, 2 times 3 is 6. So the slope of this tangent line is 1/6. Okay, now, just knowing the slope of a line is not enough information to write the equation of the line. I like to use the point slope form when I'm doing this. Okay, and if you remember, that goes like this. It's like, I guess I don't need parentheses on this side, but it's y minus y1 equals m times x minus x1. And the slope, of course, is represented by m, and the point on the line is x1 comma y1. Okay, so in order for me to write the equation of a line, I need to know a point on the line as well as the slope. Now, our slope is 1/6. Well, what's the point on the line? Well, we can just evaluate the function f of x to get the y coordinate. So, it'd be 9 comma 3, right? Because we want this line to touch the square root function at the point where x equals 9. And when x equals 9, the y coordinate is 3. Okay, so now that we've got that, we can do this. We do y minus 3 equals 1/6 times x minus 9. All right, now, I'm going to do this in a way that looks a little funny. I'm going to add the 3 over. Okay, now, the reason I'm doing it in this way is that this is going to be very useful for generalizing the idea that we're talking about. Now, of course, we can simplify this a great deal if we distribute, right, we typically write it like this. We distribute the 1/6 times 9 is 3 over 2, and it's negative. So I guess I get 1/6 x plus 3 over 2 as the equation of my tangent line. Let the ink dry there, and it'll come into focus. Okay, so pretty easy Calc 1 problem, writing the equation of a tangent line. Let me switch over to GeoGebra here. How about we make this window nice and big? It's kind of small there. Let's zoom in there so we can see everything. Whoa, whoa, whoa. Kind of overshot it there, but that's okay. Okay, so nice and big. So I want to start by graphing the square root function. So in GeoGebra, I believe the command is square root of x. Okay, so square root x. Okay, now this is, I'm going to drag the drawing pad over like that, right? There's nothing happening over here on the left-hand side of the x-axis, and there's nothing happening below the x-axis either. So here's where we are. All right, now, we found with our calculations that the line tangent to our graph at this point, and let me plot the point 9, 3. Okay, so that's plotted right there. We found that the equation of the line tangent to the graph of y equals square root x was supposed to be y equals 1/6 x plus 3 over 2. Let's see how we did. Okay, it looks pretty darn good, right? That is very close to the graph of our function at that point. Okay. Now, of course, it doesn't work when you get far out, right? Once you start to get away from 9, the graph of the function starts to bend away from the tangent line. But in the neighborhood of x equals 9, this is a fairly good approximation of the graph of our function. So let me switch back to my document camera and do a little application. And let me move out of the way here. So what I want to do is I want to approximate the value of radical 10. Right now, I don't know what the decimal value of radical 10 is, right? It's an irrational number. It's a non-terminating, non-repeating decimal. Ooh, gotta pause 1 sec. I'm gonna sneeze. Okay, that's better. Okay, so it's some non-terminating, non-repeating decimal. Don't know what it is. However, I do know that near x equals 9, radical x is approximately equal to 1/6 x plus 3/2. Okay, that's the whole idea of a tangent line. It means that near the point where we create the tangent line, our function can be approximated by the tangent line. Okay. So 10 is kind of close to x equals 9, x equals 10. So square root 10 is approximately equal to 1/6 times 10 plus 3 over 2. And we can do the arithmetic here. This is 10/6, this is 9/6, so is approximately equal to 19 over 6. So what we're saying here is radical 10 is approximately equal to 19 over 6. Let me do a little check. Okay, how did I do 19 over 6 squared? Okay, bottom is 36. Numerator, let me see, 19 squared. Ugh. Let me see if I can calculate that mentally. 20, so 400 minus 40, so 361. Oh gosh, that is very close to 10, right? Because that is equal to 10 and 1 over 36. Okay, so that's actually a fairly good approximation there. Okay, we're getting something that almost does the job for us of what radical 10 is supposed to do. And of course, the job that radical 10 does is when you square radical 10, you get 10. Okay, so this is one of the uses of a tangent line approximation. So let me switch back to that GeoGebra graph that we had set up here. Okay, so I'm going to go ahead and zoom in kind of at that point there, because the way we had it right here, it might give you the impression that the graph of the tangent line was exactly on the graph of the curve for this stretch here. It looks like they overlap. Okay, but if we zoom in here, I'm scrolling in here, I'm zooming in near that point, we can see, okay, see how it's actually bending away here a little bit sooner than we might think. Okay, so when we get to x equals 10, right, the graph is a little bit above. You see that tiny little bit of difference there. Okay, so one of the natural questions that we might ask is, okay, well, if this gives us a good approximation, is there any way to refine it and make it better? So let me make some notes about that. So the general idea what we're doing here is this. We're saying that f of x can be approximated by our tangent line. Now, I want to go back just one sec and look at this right here. You see when I wrote it in this kind of funny way, I said this is going to be useful for generalization. Okay, so let me think about where the parts are coming from. Okay, the 3 is coming from, okay, well, we added 3 to both sides, but that's not what I mean. I mean, why is it 3? It's 3 because that's the value of the function at x equals 9. Okay, so near any point C, near x equals C, f of x is approximated by f of C plus f prime of C times x minus C. Okay, now this gives us a linear function, and the key there is that it's easy to evaluate. Okay, we can compute the value of a linear function for any given x value, whereas some other nonlinear functions we might not be able to compute, but we can approximate using those linear functions. Okay, so this makes it go through, this makes the linear function go through the appropriate point, and this makes it have the appropriate slope. Okay? Now, as we saw in the graph, you got your tangent line, and then you got your function, which is a curve. Our function was bending away from our tangent line. So to make a better approximation, we need to not only incorporate the slope, but also incorporate how the function is bending. In other words, we need to look at the concavity of the function at our point. And if we think back to our calculus, there's a quantity that measures the concavity of a function. That's, of course, the second derivative. So we use the value of the function, the value of the derivative, and to get an even better approximation, we will use the second derivative. Okay. So to refine this idea, what we do oops, a little off the screen there. What we do is we use the second derivative and we say, okay, f of x can be approximated a little bit better by doing f of c plus f prime of c times x minus c plus f double prime of c. Now we're going to need to do this. We're going to need to do f double prime of c over 2 times x minus c squared. Okay, so the only way to get a function that's going to bend is you have to go up to a second degree polynomial. Okay, so that's why this is squared here. We can't just have a linear term because then we'll still have a line, and even though you've got the second derivative in there, the function won't bend. You got to have at least a quadratic to get the function to turn. And this will also make this second degree polynomial agree with the value of the function. The first derivative will agree with the first derivative of the function, and the second derivative will agree with the second derivative of the function. The reason this 2 is here is because when you differentiate once, this will come down and cancel, and then when you differentiate again, this part will go away, and you'll just be left with f prime of c, so the second derivative will agree. Okay, so this is why I think it's important to kind of look at the tangent line in this way, because it readily generalizes to a better second degree approximation. Okay, let me go back to our GeoGebra thing, and we'll do some stuff here. Okay, so we have our tangent line approximation, and if I do some computations here, let me do y equals, and I'm going to go back to kind of writing it like we were over here. Okay, so f prime of c. F of c, so our x value is 9. So if we use that in the square root function, we get a 3. So we have 3 plus 1/6 x minus 9. Okay, so that's just giving us the same old tangent line that we had before, so nothing new yet. Plus, now what I need to do is I need to take the second derivative of the square root function. Let me go back to my notebook here. So if I have f of x equals square root x, we know that f prime of x would be 1 over 2 radical x. And that's, of course, coming from x power negative 1/2. And f double prime of x, well, we differentiate again. Negative 1/2 comes down, so we got negative 1/4 out front. New exponent is negative 1/2 minus 1, so negative 3/2. So I have negative 1/4 x to the negative 3/2. So this is negative 1 over 4 square root of x cubed. Okay, if you remember your negative exponents. So I have to take this and evaluate it when x equals 9. Okay, so going back to the GeoGebra thingy. I'm going to get a negative 1 over, okay, so if I take the square root of 9, I get 3, cube it, I get 27. 4 times 27 is 108, and this would be x minus 9 power 2. Okay. Now, I'm going to mute the, going to take away the tangent line here. Okay, but I also kind of like to compare these two, right? The tangent line, let me make this a different color so we can kind of see really what's going on. So the tangent line, let's make that blue. Okay, so the tangent line is blue, and this second order polynomial is the black line. The original function is there in green. Okay, so we can see here, if I zoom in near x equals 9, notice that my tangent line doesn't bend, of course, right? It stays straight because it's a line. But that second degree polynomial, it kind of bends with the square root function, at least a little bit. Okay? So that second order polynomial is actually a little bit better approximation than the tangent line was. Okay, notice how it's kind of bending with it, at least in this neighborhood. So if I wanted to refine my approximation for radical 10, I would use this polynomial right here. I'd plug in x equals 10 and get an even better approximation of radical 10. And I hope you can see the general theme here. It would be that to get an even better approximation, you incorporate more terms. So this right here, this 3, this was the value of the function, the derivative, the second derivative. Oh, I think I might have forgotten my 1/2. I think I need 2/16 here. Yeah, that's even better. I forgot it was 1/2 the second derivative. Okay, so you get an even better approximation when you incorporate that second derivative. Okay, so that's the kind of the basic idea behind polynomial approximations. And since you can use a polynomial with as high a degree as you would like, you can, in other words, you can keep on going. You actually get a series by kind of extending by taking the limit that will approximate the function.